So let's kick off this module by painting the big picture. Imagine wake up, open Netflix, and the first show you see exactly what you have been wanting. Maybe before you even know it yourself, the moment of wow, that is perfect is not an accident. It's a result of recommended system quietly crunching mountains of data in the background. Across e-commerce and streaming, somewhere between a third or almost half of all revenue can be traced directly to these systems. They shrink a catalog of millions into a curated handful, cutting decision fatigue and building a sense of personal connection with the brand. So from the business side, the high click-through rates. The stakes are huge, high click-through rates, large basket sizes, lower churn, and stronger lifetime value. Companies leverage recommendations insight for inventory planning, dynamic pricing, even content production. In other words, recommendation engines are not just UX glitter. They influence strategic decisions all the way up to the C-suite. There's another layer that matters. Competitive moats. The best model feeds on proprietary interaction data. So once you have a flywheel that is users generating data that improve the model, which attracts more users, you build a self-reinforcing advantage. That's why new entrants find it so hard to topple giants like Amazon or Spotify. Finally, remember that personalization isn't confined to retail and media. Hospitals recommend treatment information. Universities suggest courses, and enterprise SaaS platforms surface the right file or colleague at the right time. Wherever there's too much choice and not enough attention, recommendation engines step in. Now that we appreciate why recommendations are indispensable, let's ground that idea by looking at where you experience them every single day and sometimes without even realizing it. All right, let's tour the crazy variety of places where recommendation logic shapes our lives. Open Amazon, and you will see frequently bought together bundles nudging you to add an HDMI cable when you buy a television. Scroll down, an entire carousel whisper. Customers who view this also viewed. Netflix tweaks thumbnails art, so the same show appears romance-themed to one viewer and action-packed to another, depending on what grabs each person's attention. Jump into TikTok's For You feed, and you will notice it's dangerously good at locking onto your micro interest. Maybe you are suddenly on basket weaving talk or cat reaction talk. That is the platform optimized for watch time, not merely clicks. LinkedIn runs a sophisticated pipeline to surface job postings you are likely to apply to, and even suggests people you may know, subtly incentivizing you to expand your network. Spotify fans Discover Weekly and daily mix lists are driven by embedding spaces learned from billions of listening sections. The playlists feel hand-curated, yet they are fully algorithmic. Enterprise software uses similar patterns. Atlassian or Microsoft search boxes suggest relevant documents before you finish typing. Knowledge Portal inside Fortune 500 companies recommend experts to ping when you are stuck. Even smart TVs and voice assistants like Alexa employ on-device models to suggest content hands-free. Notice the breadth of business goals: commerce, upsell, media retention, ad revenue, or internal productivity, yet the underlying task, ranking a large set of options for a specific user in a specific context, remains the same. The versatility of recommender system is precisely why they are considered an AI-powered tool. Seeing all these examples raises an obvious question: how do these platforms turn raw click logs into such laser-focused suggestions? To answer that, we need to dissect the architecture of a modern recommender pipeline. Think of a recommender system as a relay race with three main runners. The first runner is candidate generation. Its job is speed, pulling maybe 10,000 possible items from a catalog of millions in a few milliseconds. Techniques here are intentionally lightweight: matrix factorization, approximate nearest neighbor indices, or a rule-based filter that grabs, say, the top items for your locale. Once candidates are in hand, they are passed to the second rounder, heavy ranking. Hence, the gloves come off. Deep neural network, like transformer-based ranker, compute a rich score for each candidate, looking at high-dimensional user and item embeddings, plus context features such as device, day of week, or even weather. This stage whittle 10,000 items down to a couple hundreds. Finally, we reach re-ranking. Think of this as the politics layer, where business rules, diversity, and fairness step in. Perhaps legal requires that alcohol ads not dominate team timelines, or the design team wants to sprinkle in less popular but high-margin items. Reinforcement learning policies or multi-objective optimizers often handle these nuanced constraints. Around this relay race runs an ever-running feedback loop. Each impression or click is logged in real time, nightly or even continuously. Training pipelines refresh embeddings. Shadow deployment tests new models silently beside the old ones. Canary release ensure any performance hiccup is caught between rolling out globally. Getting this pipeline right is a balancing act between latency, accuracy, and operational complexity. A brilliant model that takes 1.5 seconds to respond, use this. The user is already gone. A blazing fast model that cannot beat popularity baseline, equally pointless. So components are great, but data is king. Let's zoom in to the raw material: explicit rating, implicit signals, and contextual breadcrumbs that fuels each stage of the pipeline. Data is the oxygen for any recommender. We usually talk about two broad flavors, explicit and implicit feedback. Explicit signals are crystal clear, 5-star ratings, written review, like or dislike buttons. They are great because they encode direct preference, but they are also painfully rare. Most users never bother to rate. That's where implicit feedback carries the day. Did the user hover over a product for 8 seconds? Did they scroll halfway down a page? Did they add an item to the cart but abandon it? Each micro interaction tells a story. In music streaming, the skip rate within the first 30 seconds is basically a thumb down signal. Completing a song is closer to a like. We enrich these behavioral logs with user profile feature, age bands, loyalty tier, preferred language, and item metadata such as brand, price point, texture descriptions, and increasingly learned image or video embedding extracted using computer vision. Contextual features matter too. Recommendation differ at 8 a.m. on a Tuesday commuter train versus a 10 p.m. on a Saturday couch. A heavily underrated hero is the Feature Store, a low latency service that serves the exact same engineered feature both to the rating pipeline and to the online model. That avoid the classic chaining serving skew where the live model gets subtly different input and performance nosedives. Feature engineering is both art and science. You must balance complexity with costs. Do you really need that 200-dimensional gaze tracking vector if it slows inference? Maybe not, but a simple binary feature indicating user visited FAQs in section could be priceless for customer support recommendation. With a treasure trove of data ready, how do we know if our shiny new model is actually good? That's where metrics and evaluation pipeline step up. Evaluation in recommender systems is like juggling flaming torches. Get one metric wrong, and you burn the user experience or the business model. We start with accuracy metrics borrowed from information retrieval and rating predictions, such as root mean square error, mean absolute error, area under curve. So alphabet soup that capture how well our ranker orders items according to hidden ground truth. But raw accuracy only tells part of the story. Click-through rate, like business metrics such as click-through rate, conversion rate, revenue per thousand impressions, translates models' performance into dollars and cents. For instance, a model with slightly lower AUC might still generate more revenue if it promotes high-margin items. Then we have user experience metrics like diversity, novelty, and serendipity. A perfectly accurate model that keeps showing me only Marvel movie will get boring fast. Humans crave variety. And safety metrics check the operational side, such as memory usage, error rates, because the best model in the world is useless if it times out or crashes under load. Evaluation happens in two arenas. Offline, we use historical logs for quick iteration, but log data suffers from selection bias. Users only interacted with what the old model showed them. So we run counterfactual estimators like inverse propensity scoring or doubly robust methods to approximate what would have happened if we have served different items. Ultimately, the referee is an online A/B test. We bucket users, serve different model variants, and watch guardrails metrics, bounce rates, section length to ensure we don't accidentally tank the product. A holistic dashboard then check drift and fairness longitudinally. Okay, before we dive into sophisticated machine learning models, let's ground ourselves with simple baseline, because if you can't beat a popularity list, you are not ready for prime time. Baselines are the Peter Nuts, Butter, and Jerry of recommendation science. Humble may be boring, but you will miss them terribly if they are gone. The first and oldest pipeline is global popularity, just show whatever is most viewed or purchased across the entire platform. Surprisingly, this model often performs quite well, especially for brand new or anonymous users who haven't provided any personal signals yet. It's the safety net of personalization. Next up is trend detection within segments. What's hot in San Diego might be lukewarm in Seattle. Likewise, Gen Z taste can diverge widely from Gen X. A geographically or demographically aware popularity list already introduces a hint of personalization with negligible computation. We also lean on the recently reviewed or continue watching carousel, which isn't sophisticated but leverage recency bias. That cognitive preference for items we touch last. Similarly, rule-based editorial picks or merchandiser curated collections guarantees exposure for strategic inventory like new release or sponsored products. A slightly more intelligent baseline is item-to-item cosine similarity over co-occurrence matrix. Amazon's seminar paper from 2 decades ago showed these tiny algorithms drive billions in upsells and cross-sells. It calculates how often two products appear together in transactions, then recommends the neighbor list whenever one of them is in cart. Why obsess over these heuristics? First, they define a performance flaw. If your fancy neural network can't show the most popular, something is wrong. Second, they serve as the graceful fallback during outage. If a deep model fails to load because of GPU issue, the platform can instantly revert to popularity list, preserving user trust and revenue. Third, they are transparent, making them great tutorials for busy stakeholders skeptical of AI black box. With the baseline safety nets firmly in place, let's step into our first fully personalized classic method, which is memory-based collaborative filtering the grandfather of modern recommenders. Welcome to the first classic personalization algorithm, memory-based collaborative filtering. Think of collaborative filtering, or CF, as the digital version of word of mouth. If Alex and Bob both loved Interstellar, and Alex also raved about Arrival, then Bob is probably a good candidate for Arrival as well. So collaborative filtering captures that intuition mathematically. There are two flavors. User-based collaborative filtering starts by computing a similarity score, cosine, Pearson, or even Jaccard, between every pair of users based on their interaction vectors. Your nearest neighbors are the users whose vector most resemble yours. Once the model finds that neighborhood, it looks for items those neighbors like that you haven't seen and push them to the top of your list. Item-based collaborative filtering flip the table. Items become the nodes, and we connect two items where many users interacted with both. Then you click on, when you click on Black Panther, for example, the engine simply work that item's neighborhood and serve the closest titles. Why does collaborative filtering still matters? It's content agnostic. You don't need text, image, or price, only the sparse user item matrices. That is a blessing for domain where content features are hard to engineer, like instrumental music or abstract art. But collaborative filtering also reveals that classic code start trap. New users look like empty rows. New items look like empty columns. And sparsity explodes as catalog grows. At scale, computing pairwise similarity become an bigger of n-squared nightmare. So production systems employs approximate nearest neighbor libraries to prune the search. Today, collaborative filtering rarely runs solo in consumer giants, yet it lives on in hybrid stacks and as a sanity check baseline. It's transparent users who like this also like that logic is marketing friendly and easy to debug. So collaborative filtering laid the groundwork, but its matrix can only take us so far. To tame sparsity and scale elegantly, we graduate to matrix factorization, our next stop. Imagine complexing a big job, mostly empty user item grids into two compact sets of vectors that magically preserve preference patterns. That is matrix factorization in a nutshell. It posits that any interaction score can be approximated by the dot product of a user embedding and an item embedding living in a low-dimensional taste space, maybe 32 or 128 dimensions instead of millions. The workforce algorithm is alternating least square or ALS, keeping items vector fixed, solve for user vectors, flip and repeat until convergence. For ranking tasks, Bayesian personalized ranking swaps square error loss for a pairwise objective that explicitly favors correct ordering. Variants like SVD++ add implicit feedback term so that just viewing a movie nudge its latent signal. Why is this magical? First, it handles sparsity by projecting everything into dense space. Even a brand new user with 3 ratings get a meaningful vector. Second, embeddings reveal hidden semantics. One axis may represent quirky indie versus mainstream blockbuster, another short form versus long form content. Product teams may visualize these axes to spot catalog gaps or cluster similar items for campaigns. Operationally, embeddings enable bracing recall, that is to push all items vectors into a vector search index and retrieve top K with an inner product. No full matrix scan required. Real-time updates are tractable while incremental SGD, stochastic gradient descent, or streaming ALS alternating least square. No, so the system may never drift far from current taste. So what are the limitations? Factorization assumes linear interaction, great for first-order taste, but blind to higher order. Nonlinear features clauses. It also struggles when metadata matters. 2 distinct items with identical interaction histories collapse onto the same vector. So factorization conquered sparsity, but sometimes user intent hinge on the item itself, its text, images, or attributes. That set the stage for content-based filtering. Content-based filtering flips the lens from who likes an item to what the item actually is. Picture using TF-IDF or BERT embeddings to encode every movie's plot summary, or using clip to represent album art as a vector. When a user enjoys a movie, the engine searches for items whose content vectors cluster near that movie. The CUDA feature here is cold start for new items. The moment a brand new sci-fi novel is published, it inherits a descriptive vector even before a single reader reads it, so it can surface to the right audience immediately. Likewise, if a user only ever interacted with 3 vegan recipes, you can still recommend more by matching ingredients and cooking style. But there's a catch. Without collaborative signals, the model risks an echo chamber, continuously feeding users near identical contents, shrinking discovery. Hybridizing with collaborative filtering or factorization injects cloud wisdom and breaks the loop. Tech stack highlights. Classic bag of words with cosine similarity is still shockingly strong for short texts. Dot to vec or sentence transformer embeddings capture semantic better. For images, ResNet or Vision Transformer features work great. Audio embeddings from Wave to WAG handles podcasts. The retrieval layer mirrors factorization. All vectors live in an ANN index, supporting millisecond similarity search. Explainability come almost for free because this recipe also uses chickpeas and tahini, or because these films share the same director and cyberpunk genre. Such attributes level feature build trust and align with emerging AI transparency regulations. No single method rule them all. To balance strength or weakness, industry leaders blend collective filtering, factorization, and content signals into hybrid system, our next focal point. Hybrid recommenders are the avengers of personalization. Each algorithm brings its superpower, covering teammates' blind spots. There are three popular fusion patterns. First one, model-level fusion. Train a multi-tower neural network when one tower injects collaborative filtering embeddings. Another injects content vectors. Maybe a third process knowledge graph features. The outputs merge through concatenation or attention before the final score. YouTube's DeepMind multi-gate mixture of experts is a flagship example. Second, ensemble-level fusion. Run independent models, say a popularity baseline, and a BERT text match model, then combine scores while weighted sum, rank branding, or learning to rank meta models. This is easier to iterate on because you can hot swap components without retraining everything. Bandit style gating is to use a contextual multi-armed bandit or reinforcement learning policy to select per request which expert model or slate to serve. If the user's history is sparse, favor content-based. If rich, lean on collaborative filtering. This dynamic routing maximizes rewards, such as click-through rate, watch time in real time. Hybridization boosts robustness. The system degrades gracefully when data sparsity, adversarial attacks, or feature outage happen. It also supports multi-objective goals. Fairness components can re-rank the final slate for exposure parity. While a graph model injects diversity, there are some implementation tips. Align feature scales before branding scores. Monitor each submodule's contribution with sharply value audits to avoid silent drift, and keep latency budget realistic. Parallelize inference wherever possible. Our hybrids increasingly rely on neural network to juggle vast categorical feature space. Let's drill into the specialized deep models that dominate ad tag and feed ranking. Deep learning entered recommender land not through image or text, but through humble tabular data. Billions of rows of user IDs, item IDs, and context flags. Google's wide and deep architecture pioneered a pragmatic mix, a linear wide branch memorize frequent feature clauses, such as user 123 plus item 456 often click, while a deep branch, a multi-layer perception over embedding, generalize to unseen combos. Joint training lets the two exchange gradients, yielding the best of both worlds. Deep FM marries a factorization machine layer to a deep tower, removing the need for manual feature classes. It reuses the same embeddings, slashing memory and training time. And deep and cross network go further. Deterministic cross layers compute high order interactions explicitly, capturing patterns the multi layer perception might miss. Key enabler is embedding tables. Each categorical tokens, users, items, campaigns, zip code map to a dense vector. For trillion entry tables, sharding across GPUs or TPU pod is mandatory. Mixed precision, like FP floating point 16, halves memory with negligible accuracy drop, and CUDA graphs shave milliseconds of inference. So why choose neural tabular models? First, they are feature hungry. Throw in weather, device battery, or even histogram stats of past sections. And then the network figures out synergy. Second, they integrate seamlessly with ad bidding pipelines, where MIDI sends improvements scale to billions of dollars. But transparency can suffer. Post hoc tools like Sharp or integrated gradients estimate each feature's contribution, helping compliance teams answer why was this ad shown, vital under transparency requirements. Scaling user and item vocabularies to the billions push these models to the brink. Meta's model rose to that challenge. Our next deep dive. So Meta's deep learning recommendation model, DLRM, deep learning recommendation model, was purpose-built for industrial scale. Think trillions of training examples per day and embedding tables dwarfing GPU memory. The recipe is to embed every sparse feature, apply feature interaction, dot products, or concatenation, then pass the concatenated tensor through a deep multi-layer perception. Several engineering tricks made DLRM, deep learning recommendation models, production ready. Embedding bagging groups lookups from the same table, reducing memory bandwidth. Quantization strings tables will retain accuracy, especially when combined with per channel scaling. CUDA graphs pre-record kernel launches, slicing latency below 2 milliseconds. Research iterations burst DLRM2, transformer interaction layers instead of simple dot products, residual connections stabilizing very deep towers, and self-supervised pre-training on massive unlabeled logs. Other cousins include deep interest network for e-commerce ads, which uses attention over historical clicks. Serving this behemoth demands a dedicated stack. Feature stores dispatch real-time features. Inference server batch GPU requests, and parameter servers are embedding sharding distributes tables across dozens of nodes. Hot embeddings live in GPU. Cold ones swap in from NVMe. Performance gains are staggering. Double digits click-through rate lifts are common when migrating from wide deep to deep learning recommendation model. However, compute costs skyrocket and carbon footprints draw scrutiny. Techniques like embedding pruning, distillation, and on-device caching aim to keep budgets sane. Addictively, deep learning recommendation model sheer capacity can amplify bias if training data skews. Fairness-aware training, exposure-balanced losses, and calibrated probability output help mitigate harm. With these tools powering feeds and ad stacks, our next frontier explores sequence-aware and transformer models. Up to this point, most of our models have treated user history as an unordered bag or at best a static profile. But real behavior is sequential. You watch a trailer, then click cast interviews, then search for merchandise. The order and recency of those events screen intent, and transformer-style models are the state-of-the-art way to capture it. Let's start with self-attention sequential recommendations. It chops a user's last n clicks into a token sequence, adds positional encoding just like original BERT, and uses multi-head self-attention to predict next item. Because attention can look both at short and long distance, the self-attention sequential recommendation detects micro trends, such as just started binging K-dramas, and macro taste generally like psychological thrillers. And but for RAG, up the game with a bidirectional objective, randomly mask 15% of the items and force the model to reconstruct them, giving full left and right context. On dense logs, think daily music listening, but for RAG handily beats RN and CM. Industry variants abound. ByteDance's M6 T-RAG feeds watch time as token weights. Amazon's T-time integrates dwell-time gaps as learned time difference embedding. Pinterest's Pixie transformer mixes graph works with sequence attention. All share one trait, the ability to update embeddings online. Streaming feature pipelines append the newest click, runs a single forward pass, and voila, real-time personalization in under 50 milliseconds. So these are the serving tricks. Maintain a cached key value memory for the attention layers. So each new event only add one step of computation. Distill the big model into a four-layer student for mobile. Or pre-compute section embedding and treat them as user IDs in downstream rankers. Why bother? Because sequence model boost short-term CTR, click-through rate, up to 15% on feeds where recency rules like news short videos, grocery reorder. They also improve diversity because transition uncover niche interest you'd miss in static profiles. Okay, we have built dazzlingly accurate model, but how do we surface their output in interfaces people actually trust and enjoy? That's the realm of HCI. A perfect algorithm hidden behind a confusing interface is a wasted opportunity. Human-computer interaction research reminds us that recommendation quality is perceived, not just logged. Let's unpack four pillars: trust, control, accessibility, and cognitive loads. Trust and transparency is the first. Users often wonder, why am I seeing this? Or simple explanation widgets, such as because you like Inception and another sci-fi thrillers, boost acceptance and reduce creepiness. A/B test at Netflix showed that even one-line rationale cut title rejection by 10%. Under the EU's AI Act, such transparency will soon be a legal must-have. User control is the second. Give people adjustable dials like skip, thumb down, show me less like this. Spotify's hide this song and TikTok's not interested button feed negative feedback loops, speeding convergence to satisfying contents. Power users appreciate deep dashboards listing their inferred genre or topics, letting them delete or reweight interest in increases long-term retention. Third one is accessibility. Voice-first service like smart speakers, in-car systems need recommenders that can summarize slates verbally, not scrollable grid for visually impaired users. Alt text explanation plus smart ordering reduce navigation time. Meanwhile, gaze tracking on VR headsets can provide implicit activities, such as looking away quickly, that model can learn from. And then first, cognitive loads. Presenting 200 ranked items in one endless colossal overwhelms. Progressive disclosure show top 5, then a more like this accordion keeps the interface breathable. Diversity aware regarding re-ranking ensures variety. Mix a broad buster, a niche pick, and a wild card, for example. Studies show decision satisfaction peak when choice set 7 plus or minus 2 items. Implementation tips include collaboration with UX early, instruments front-end event such as scroll, depth, hover, pause as extra model signals. and continuously text copy text, such as recommended for you versus because you watched, because micro wording stripped click through. Designing for delight is wonderful, but power cuts both ways. Left unchecked, these systems can entrench bias or nudge behavior unethically. So, you might have heard about the motto of move fast and break things. It isn't good enough for recommender systems that mediate culture, commerce, even elections. Let's anchor on three risk categories: bias and fairness, privacy and manipulation, then outline guardrails. First, let's look at bias and fairness. Exposure bias means popular items get shown more. Snowballing advantage, minority-owned sellers, or indie musician language. Mitigation strategies include re-ranking for equity, such as ensuring at least 30% of Slate's impressions go to long-tail creators, and fairness-aware loss functions that penalize skill during training. Regular disparity dashboards break metrics down by seller type, gender, region, flagging drift, and privacy. With regulations like GDPR or CCPA, European and California privacy regulation, user data is on loan, not owned. Techniques such as federated learning keep raw behavior on device, shipping only gradients updates. Differential privacy adds calibrated noise to embedding, thwarting membership influence attacks. Policy teams must define data retention windows and on the right to be forgotten request, embedding timestamp included. And next is manipulation and well-being. Optimize it exclusively for clickbait, and you risk rabbit hole that wreck user welfare. Platforms like YouTube have introduced long-term satisfaction reward signal, survey responses, section quality heuristics to discourage doom scrolling. Reinforcement learning agents can integrate dwell time and post-watch satisfaction, balancing short versus long horizontal payoffs. In terms of transparency accountability, publish models cards, state objective, data source, non-limitations, offer downloadable personal history so researchers can audit echo chambers. Establish a model review board, engineers, ethicists, legal sign-off before major changes roll out. Next is incident response. Maintain queue switches. If metrics spike abnormally, revert to safe baseline. Run chaos drills where embeddings go stale or a feature store drops. Observe recover time. Finally, culture matters. Reward team not just for CRT lift, but for meeting fairness and retention goals. Ethical recommender systems aren't slower, they are sustainable. Building them user trust, mitigates regulatory fines, and frankly, let us sleep at night. So we have journeyed from popularity list to transformers, from UI haptics to policy guardrails. Your takeaway is great recommender system equal great engineering plus great responsibility. Go forth and personalize wisely and responsibly.